chapter 10. Chapter 10 is the first chapter of Unit 3. And technically the unit is supposed to go through chapter 12, so 10, 11, 12. I believe that we'll only be able to finish chapter 11 this year, but which means you will have gotten about 2/3 of the chapters that we would have covered this year. So apologies for the slow pace with the every other day nature of school for a very long time, and then half day nature. And anyway, all that to say, sorry that as far as what I have said hasn't covered everything that you should learn. But do remember that you all have checked out to you textbooks, and you're free to read ahead. You are free to read ahead. So do not adopt the attitude, well, my class didn't grade it, so it wasn't important. That is not true. Okay, not everything that is important is graded. Hopefully, everything that's graded is important, and of course, not everything that is taught is graded either. So, are you guys familiar with Venn diagrams? Right. Are you familiar with Euler diagrams? There was a mathematician, Leonhard Euler from the 1700s. Have you ever heard of him? He's the one that came up with the number E. You know about E? Not E equals MC squared. It's lowercase e. You know E? No? Have you guys studied logarithms yet? All right. Eventually get to E. Ask your math teachers about E. It's kind of like pi. It's this number that has meaning based on other things happening. Anyway, he came up with E, and he came up with a bunch of things. But the Venn diagrams are equally sized circles, and they're usually 2, but they could be 3 or whatever. Euler diagrams, you could have one circle all the way inside another circle. They can overlap. They can be separate. They can be one inside the other. Can I help you? Oh yeah, Isaac, welcome. You're still listed as remote though. Can I? Yeah. Yeah. That's what threw me by surprise the other day too. Not that you're not welcome, but I just want them to know that you're going. Which office is it, Kevin? Yeah. Sorry for the delay. 17th. No. Yes. Okay. Yeah, get them to flip the switch in the computer to say you're in person. Thanks. Okay. Now, where were we? All right. What were we talking about? I lost the train of thought. What were we talking about? Oh yes, the Euler diagram. So, when you are doing anything with logic, something may be completely within another thing. So everything that's graded should be from what is taught. Okay. There shouldn't be anything graded that's a gotcha, like, we're never even slightly addressed it in class, but I'm going to grade you on it anyway, unless it's extra credit. Extra credit is always extra credit. But then outside of that, not everything everything that is taught should be something worth learning, all right? But there's not enough time in the day to cover everything that's worth learning, so we select some things and not others, okay? And everything that's worth learning belongs to what is true, hopefully. Hopefully you're not getting falsehoods, certainly nothing intentional. Okay, back to the slideshow. Percent composition from the chemical formula. Now, we talked last week about how you can look at a formula and or measure mass, either way, and you can get percent compositions there. You can, let's say, that 5 grams is from oxygen. The whole thing weighed 15 grams. So the percent composition would be 33% is oxygen, 10% is something else. Okay, maybe you don't know what the other thing is, but at least 33% is oxygen. And then or if you had a formula like iron 3 oxide, which is basically rust, iron 3 oxide. So that'd be Fe2O3, because to be iron 3, it has to balance out oxygen, which is -2. So you have to have 2 of one, 3 of the other. Makes them a total charge of 6 and 6. So anyway, with that, if we add that up together, it's about what is that? 53, 55.8. Okay, so let's just round to 56. 56 grams per mole for oxygen times 2 is going to be 112, plus 3 oxygens at 16 each, that's another 48. So 48 and 112 is 160. So 48 is about 50, I'm rounding here, and 160 is about 150. So that's about, and it's not really, but it's about 33% or 30%. Because I rounded so much, let's just go to the nearest tens. It's closer to 30 anyway than it is to 20% or to 40%. So 30%, just one significant figure. But you can just quickly do that without really pulling out a calculator. You just do need to have access to the periodic table. I do expect you to know that oxygen weighs 16. Once you get past the third period, though, they become less and less necessary to know the masses. But those non-metals, especially, they come up so much. It's good to know those. All right, let's see here. So knowing its chemical formula, I can get those. So about 30-70, 30% oxygen, 70% iron. Even though iron, as far as atoms go, is only 40%. So it goes from 40% of the atoms, the number, to 70% of the amount, all right? And that's all because in the nucleus, there are more protons than neutrons. So, again, this is how you do it. The mass of the element in 1 mole of the compound divided by the mass of the compound times 100. That's exactly what I just did there with the oxygen. Okay, so we got propane. We work through that. We've got carbon. There are 3 moles of carbon in propane, 8 of hydrogen, and you get a total of 44. We've gone through this. And again, just to review here, the units drop out, so we just have a percent. And again, if you're not paying attention to the units, then you're going to plug in the wrong numbers. But your units should drop out, and the only thing you should have left as a label is identifying what the thing is here, right? The carbon. So because you have a C up here, you need to have a C down here. All right? Don't get confused what it is. And then as you work through, then you get percent. Percent isn't really a unit or a label. There we go. Okay. Now, again, hydrogen, you could have just done subtraction, but if you did that, then you wouldn't have actually gotten the exact number that you get here by plugging in the numbers that are through the multiplication and division. So 18.3 versus 18.4, does it really matter? Not really. But if you do, because when you do round it, it rounds to 2 sig figs to 82 and 18 either way, whether it's 18.4 or 18.3. All right. Now, as a conversion factor here, we've gone through this as well. I'm not going to repeat all this for you. But the conversion factor, I'm going to be using big parentheses. The slideshow does not. The slideshow does not use big parentheses, but imagine big parentheses here. And this is just a ratio. It does not have to have grams of carbon in the numerator. It could be in the denominator. It depends on what you're starting with. So if you know you're starting with so much carbon instead of so much propane, then you would flip this over. Okay, it's just a relationship, and either one can go either way. Okay, again, with the hydrogen, you know that if you had a total of 82 grams of propane, 15 of it is hydrogen. I just burned some propane last night, in fact, on purpose. Grilled some hot dogs. So, all right. So again, you've got to know the masses, and you've got to know, or you've got to know the formula. It really does help. Either way, you've got to know the molar mass of the compound, or sorry, the atomic weights, rather. Those things, you've got to know what's on the periodic table, or you're gonna have problems. Using this information, how can you calculate the empirical formula of the compound? So let's say you have certain percentages. What's the formula going to be? So if I had 15 grams of hydrogen and how many grams of 67 grams of carbon, then what did I have? 15 grams of hydrogen and 67 grams of carbon. What I have, you will be able to know that it was propane that you had. Okay, so working backwards. The empirical formula of a compound gives the lowest whole number ratio of the atoms or moles of the elements in a compound. May not be the same as a molecular formula. So, what's a molecular formula? Molecular formula is what the thing actually is. So, for instance, sucrose is made of two different, you guys know what sucrose is? It's sugar, okay? Just like sucre, right? Sucrose ends in os, that tells you it's a sugar. Anyway, sugar is made of two other simpler sugars, glucose and fructose. Have you heard of those two? Yeah, glucose and fructose. Glucose has the formula C6H12O6. There are literally 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. However, that's not the lowest whole number ratio because I can factor out a 6 from each of those, and I can get 1 C, 2 H's, and 1 oxygen. That would be the empirical formula for glucose, CH2O. But literal CH2O is something very, very different. Now, does anybody know what CH2O is? It's something you don't want to breathe. It's formaldehyde. Formaldehyde. Okay? Formaldehyde is used for what?
You told me to come back and she said that she'll figure it out.
She'll figure it out? Okay. Come back when? Come back when, Isaac?
She said that she'll call me down.
Oh, she'll call you. All right. Sounds good. All right. So, formaldehyde and glucose, one of those you want to put them in your body, one of those you don't, at least not while you're alive. But they have the same empirical formula. So it's just the ratio, 1 to 2 to 1 for carbon, hydrogen, oxygen. So, but what is formaldehyde used for? By the way, Isaac, can you charge your computer, but then sit over here behind Mason? Sorry. It is used for medical stuff. It's used for preserving biological things so that they don't rot. Because it is such a poison that even bacteria can't eat the dead material. Okay, so oftentimes in the past, there would be dissections you would do in biology class. Now they've gotten moved out into anatomy and physiology class, which you may or may not take. But you would do dissections in that, and that would be, a lot of the things would be preserved in formaldehyde. It's really stinky. And just breathing it isn't going to kill you, but it doesn't smell good. It doesn't smell good. Now there are other ways to preserve those specimens, and besides, you don't do it as a freshman anymore anyway. So, all right. But it may be the same, or it may not be the same as the molecular formula. CH2O is the exact same as the molecular formula for formaldehyde. But it is very different for glucose. Glucose is what your brain runs on. So if you didn't get any breakfast this morning, as I mentioned earlier, you do not have enough glucose floating around in your blood. You may have some starches stored up in your cells that your cells are breaking down to make glucose, but your brains probably are not working as well as those who had breakfast. No offense. All right. So hydrogen peroxide and oxygen is HO. That's the empirical formula. H2O2 is what it really is. And HO, by the way, is a thing that can exist, but it's even deadlier than H2O2. And in fact, H2O2, when it contacts other living tissues, that's what it breaks up into, is 2 of these guys, which then rip apart whatever they come in contact with, which means your skin might get a little hurt and sting, but the bacteria that are trying to get in under your skin at a cut don't. They are totally ripped apart and dead. So yay, hydrogen peroxide, those little scrubbing bubbles. All right, but the ratio is the same, 1 to 1. All right, now CO2. CO2, you're going to have just exactly what it says, carbon and 2 oxygens. It's not C2O4. I'm not even sure that can exist. No, you got to have some hydrogens in there for that. So it is literally 1 carbon, 2 oxygens, and they're floating around. And we've measured this. It is actually that many things. So you have a mole of it, then that means that you have 6.022 times 10 to the 23rd carbon dioxide molecules. And so you can break those up if you wanted to into that many carbon atoms and twice as many oxygen atoms. So here we have ethine, C2H2, and styrene. Okay, so acetylene torches and packing peanuts, same empirical formula. Same empirical formula, 1-to-1 between the C's and H's, but very different stuff, right? Do you ever see somebody try to burn packing peanuts in order to weld things together? Morning, Garrison. No, you haven't. Have you ever seen anybody weld anything? Okay, that's good. Start with that. Yeah, welders are not going to use, even though it's the exact same empirical formula, it's the same ratio, and it'll burn. I mean, you can burn packing peanuts, it'll burn, but you're not going to get what you want out of it the way that you do with ethine. And acetylene releases so much energy and is a gas because it's very light and it's got 3 bonds between the 2 carbon atoms. And those bonds are pretty high energy. And when it reacts with the oxygen to make CO2 and water, just like all hydrocarbons do, the new bonds have much less energy. They're much more relaxed. Well, that energy all has to go somewhere, and so it goes out as flame. And then it can actually speed up those metal atoms that it comes in contact with so much that they become liquid momentarily, and then they join together and mix, and then you've got your weld. Anybody in here actually taking a welding class or planning to? Okay, but if you do, that's probably what you're going to be using as acetylene. There are other ones, other torches, but it's good for welds. All right, so but we can at least figure out the empirical formula and then go forward. So even though it's not the end-all be-all as we see here, at least we can get to the empirical formula, and then we'll work on the molecular formula on another day. So we get the ratio of the masses, and then we can, if we know what the element is, we can get the number of moles and then get the lowest whole number ratio. Folks, this will take calculation. It will take paper. You can't juggle all these numbers in your head. When you are doing calculations for this, you will need to use paper in order to keep things clear in front of you. I haven't gotten to one yet. Ah, there we go. So it has 25.9% nitrogen and 74% oxygen. What's the empirical formula of the compound? And this is just a binary molecule. Right? It's just nitrogen and oxygen. So they're starting off gently here with you. 25% nitrogen, sorry, 25.9% nitrogen, and 74.1% oxygen. All right. Anybody want to take a guess what the empirical formula is? Remember, these percentages are mass. These are mass percentages. We're talking about grams per mole. Just want to take a guess? Well, you know the oxygen is going to be a bigger part, plus oxygen is heavier. How about let's just take a stab and say NO2? Say NO2. It's going to have to be a whole number. I'm probably wrong, but take a stab, okay? It's good to take a stab because, you know, hypotheses are a big part of science. So that's not your answer. It may be very far off from the answer, but let's give it a try. So first thing we have to do is, like they said, we have to change what we know about mass, which we can measure in a lab, then using the periodic table, which thankfully Mendeleev and a bunch of other people put together. Cannizzaro came up with the right way to measure molecular or molar masses. We use that number and do some calculations. Once we've done the actual measuring in the lab. So again, we write down what we know, which I just did, and it's going to be N something O something else. Now let's convert it into moles. There we go. Not that one. There we go. All right. Using the molar mass of nitrogen, grams per mole, you might say, but Mr. Bowden, it's moles per gram. Yes, I know, but you can flip these conversion factors depending on what you need. So we're starting with grams, so I want grams on the bottom. So grams per mole, and you get 1.85 moles of nitrogen. I'm skipping that on my board for space. And oxygen gets us 4.63. Oops. Notice that we're keeping 3 sig figs as we go along. But if you wanted to in your calculator, you could keep more and more digits as you go along. It won't be necessary because your answer is going to be whole numbers, probably just 1 sig fig. But it's just good for practice to keep your numbers as precise as possible along the way. Now that you know the moles, what do you think about this? Anybody think this is the answer? N 1.850 4.63? No. Can I just round it? 1.85 rounds to 2 and 4.65 rounds to, or sorry, 4.63 rounds to 5. I'll just round it. You might get lucky and have that work. Austin, can you keep your head down? Huh? Oh, okay, that's fine. You might get lucky, and that might be the actual answer, N205. But that's not how you do it, okay? What you want to do then is you want to take the bigger number divided by the smaller number, which again, you might not know right off without using a calculator. So you will need to use a calculator for this. 4.63 divided by 1.85 should give us a nice rounder number. Mason? What? Were you just doing that calculation back there on your computer? Okay. 2.50. Now that's a nice number I can work with. What is 2.5 in an improper fraction? Well, it's 2.5 with the mixed fraction, yeah. But if I don't have the whole number in front, just give me a really big numerator. 5 over 2. 5 over 2. I'll just go ahead and say it was 2.5 to start with, and then I'll do the whole multiply and add thing, and I get 5 halves, right? So the actual ratio then is, as we could have done luckily by rounding, is actually N2O5, which is really close to NO2 if this was N2O4, but it's not NO2, so scratch that, circle that. That's my answer, N2O5. Yes?
So is that because we rounded up, or is that because we didn't round up?
It's because we did the ratio. Do not just round these, okay? Do not just round those. You want to take the bigger number divided by the smallest number. Now, in this case, there's just 2 numbers, but sometimes there will be 3 numbers or 4 numbers. You always want to take all the answers divided by the smallest number and then look at it and like, well, 2.5 isn't a whole number, but it really can quickly be found 2 whole number ratio, 5 to 2.
Wait, so you said take all the other numbers and then the small numbers. Did you add all the other numbers together?
Do not add all the other numbers together. So you're going to do it separately several times, okay? So let's say that there was a carbon in there and the carbon was, 3.81 or whatever. Then you would take the 3.81 divided by 1.85, and I just made that number up, so it's probably something really ugly. But, and then you'd go from there. Okay, so, and we'll get to that, but for now, with the binary compounds, you just take the bigger divided by the smaller. Okay, so bigger divided, so obviously, itself divided by the smaller number is 1, 2.5. So we're to 2.5, and then finally this is how they did that. Fine. Just kind of plug in a 2, and then you get 2 and 5 to make sure you have whole numbers. So you can do it that way. I prefer to do it where you make the improper fraction, but different people, you know, different exact methods. As long as you know it's about ratios. All right, and does it make sense? Does it make sense that you've got 5 oxygens in there? Okay. Does it make sense that I've got 2 nitrogens? Right. I'm never going to want a fraction in there, so it's got whole numbers. Okay. And if I run it back through, 5 oxygens, it's going to be 5 times 16, which is 50 plus 30, 80. All right. And 2 nitrogens is going to be 28. So 28 and 80 added up to be 108. 80 divided by 108, yeah, it's going to be like 70-ish. Yeah. So it makes sense. All right. Can you determine the molecular formula? Yeah, you can determine the empirical formula, okay? The empirical formula. It might be the same as the molecular formula, like formaldehyde is CH2O, or it might not, like the empirical formula for glucose is CH2O. But you need more data to be sure of the molecular formula. So we're going to focus mostly on the empirical formula, and that's it for today as far as the slideshow goes. The last 15 minutes or so, please work on, maybe some of you are behind on the skill sheets, or you have other questions you'd like to ask. I'm going to go ahead and stop the recording now.